one more example, which again, this particular example could be done with methods of advanced functions. You do not need to utilize calculus methods here again, but I will show you the calculus methods to reiterate how the methods work. So what we're going to do is factor the top. So there's a GCF. To factor the bottom, we need to utilize rational root theorem. So all the possible factors or divisors that go into 2, which is plus or minus 2 or plus or minus 1, all over all the divisors of the coefficient in front here, which is 1. By trial and error, you'll notice that g, by the way, g, I named the g to be just the denominator so I can quote it. So g of 2 ends up being 0. So x minus 2 will have to be a factor of this denominator g function by the factor theorem. Then you can proceed to do synthetic division. You should get the remainder of 0 here. If you didn't, then there was a mistake. And so rewriting this denominator function g would be the x minus 2 factor and your quotient that comes from the coefficients in here. Next, we can record this denominator in its factored form, and we notice that this factor on the top could be divided out with the one on the bottom. So that implies that there is a whole at x equals 2. So if we remove that factor, we have this simplified version of the equation. And in order to find where exactly the whole is located, the y value, you want to take this 2 and put it into the simplified version. Because if you try to put it into the original, you'll get something undefined. So 2 plugged in, so 2 cubed is 8, so 8 is on the top, and 2 squared is 4, minus 1 is 3, so that's 8 over 3. Finding your y-intercept, you could substitute x equals 0, you get 0, 0, so from now on just keep working with the simplified version. To find x-intercepts, you plug in y equals 0, it's the same point as before. To find vertical asymptotes, you're going to take the denominator x squared minus 1, and you're going to solve when is it equal to 0, or you're trying to exclude those values for vertical asymptotes because they're restricted. And you find that you get -1 and +1. In terms of behavior near vertical asymptotes, both of these factors have a power of 1 or degree 1, so it's odd. So the behavior near VAs will be kind of like odd symmetry graph. So either on the left it will go up and then down on the other side, or vice versa. We'll decide how it gets put together later. Then, end behavior. This particular example will actually have an oblique asymptote because this is a rational function. And we notice that degree of the numerator, so degree of the numerator in the original is degree 4. It is equal to the degree of denominator plus 1. So the degree of the denominator is 3 plus 1 is 4. You could have also used the simplified version. It's the same thing. Degree 2 plus 1 gives you the 3. So whenever that equation right here is satisfied, you will always have an oblique asymptote. Now, to find this oblique asymptote, you have to do long division. So a quick reminder, when you're doing long division, you might have to fill in the missing terms with zeros so that everything lines up nicely. And so you would get the following result. So this equation could be written in a different format where you have quotient plus remainder all over divisor, or just over divisor, just this term, not all over, sorry. So, quick reminder, once you do the division, that's called a quotient. What you were dividing by is called divisor, and over here we get the remainder. Going up here, this is the result of this equation. So this equation over here is equivalent to that one. This term right here will go towards 0 as x goes to infinity, because the values on the bottom is going to be a bigger infinity than the ones on top. And so this could be considered as negligible in comparison, as x values are very huge. So whatever is left over is going to be our oblique asymptote. Okay, so if we were to take this oblique asymptote and jot it in, y equals x, then we could take this whole, plot it. We can take these VAs, plot those. I forgot to say the behavior near the x-intercept. So just quick reminder over here, because the x equals 0 came from the top and the degree here is 3, that's odd degree, and it's going to resemble a cubic graph. So it's going to have potentially some sort of saddle over there, or maybe it's going to be a flipped version. We'll figure that part out after. So continuing on, so I kept everything that we have so far on the graph. We're going to go on to the first derivative. Actually, quick reminder, in advanced functions, you could have finished this graph right here by testing out whether the values will be positive or negative and just finishing it off over here. But I will continue on to showcase the algorithm all the way through with this example. Okay, so using the first derivative, we're going to find, first of all, I'll record the simplified version so that I could easily find the derivative for it. So this particular one, I have a low derivative of high minus high derivative of low all over low squared. And then I have a common factor pulled out and then simplified. So critical points. Numerator could be 0 when x equals 0, so that's one of the points. And this could be 0 when x equals plus or minus square root of 3. These are the approximate versions of square root of 3. And these values, quick reminder, I find them by taking the plus or minus root 3 and putting them into the original function. Either the original or the simplified version would do the trick. Then we're going to find critical points from the denominator. We don't have piecewise, so I'm going to ignore that part. So the denominator piece right here, we have x squared minus 1. That gives us x equals to plus or minus 1. But we already remember that these are RVAs, so I don't have to say that these are critical points. So the only critical points we have is these three right here. For this example, I'm going to skip this. Moving on. So we have here, when I was trying to plot these points here, I wanted to find out exactly where the hole was. So in comparison, where do I plot the critical point? So the hole as a decimal value is written here, and you can see that it's just slightly higher than the critical point value. So I've tried to do my best to record it. And we have horizontal tangent at both of these critical points. And here as well, I should have put that in, but just imagine there's a horizontal tangent as well here. Next, I will keep my graph. I will keep my first derivative, and then to save time, here's the second derivative. And from the second derivative, we're going to do, again, the same thing as before. To find possible inflection points, we can find where is the second derivative equal to 0. Well, that happens if x equals 0 for this factor, and this factor will never be equal to 0 for real numbers. And possible inflection points can be when the second derivative is undefined or does not exist. That happens when we have x equal to 1 or negative 1. Taking all of these values, these three right here, and plotting them on the number line to fill in this chart. Okay, so the factor from the second derivative 2x is over here. So if you take any value of x's below negative 1 and put it inside here, you will have a negative value. Here is still negative, here becomes exactly 0, then positive after that. This parabola is always positive. So put that in, it's never 0 either. This parabola is opening up, so it's going to be negative on the inside of its zeros. So this infinity is placed there as a reminder that it came from the denominator, okay? And it's positive on either side of those. Because all three of these factors are either multiplied or divided, notice over here, then we can say that negative multiplied by positive divided by a positive with the cube, I know there is a cube here, but that's not going to change its sign, overall is a negative. So that means the original graph is concave down, etc. You can see how that goes. Now, decide which are actual inflection points. Well, we have x equals 1 and -1. We know that these are the vertical asymptotes. And the only other point here is this one at x equals 0, which is an actual inflection point. So, to classify critical points using second derivative, you'd have to look up your critical points from the prior slide, or that's why I left this one here so you could verify that these are correct. This x equals 0 came from the numerator, so it has a horizontal tangent there, and it happens to be an inflection point itself, so it's going to be this saddle point. Remember, we already said that the behavior near this will be like a cubic, so we already knew that. This is just to show you how you could analyze it using calculus. This particular one, again, came from the numerator, so horizontal tangent, so it's flat slope. And this value here is 1.73. 1.73 is in this region here, which is concave up region. So we have a flat slope concave up. So we'll have a minimum turning point at this value. Similarly, horizontal tangent concave down will be a maximum turning point for the x equals -3, or -√3. Okay, so with this information, we can sketch things. So this region here is concave up, going through the hole and the minimum turning point. And this is concave down, and there is a max turning point. Here we have concave down on this side of 0 because of that, and concave up on the other side of 0, like we said, is going to be a saddle point. Now, to tell you the truth, all of these steps could have been avoided. We could have done this from advanced functions. So let me just recap a little bit how you could have done that without calculus. So I'll go back to the slide that we had previously. So let's say that's the only thing you were working with, just the original function, no derivatives taken, okay? So just a quick reminder, here we found hole, we had found an x-intercept, we found the VAs and an oblique asymptote. So you could have drawn here the fact that we have a hole up here, that means the function has to go through it. And because we didn't do the derivative, we don't actually know where that turning point is. So it looks like it turns at this hole. We don't know that little detail. And in advanced function course, we never really cared about that. Then, because this particular VA at 1, we discussed the fact that it's an odd symmetry VA, the behavior near it will be the following, this one right here. So because on one side here, sorry, this one. So on one side is going up, on the other side it will come down. And we do know that the behavior near 0 here is going to be like a cubic, so we draw the cubic upwards again. And then there is another VA of odd symmetry, and so we know this other piece has to come down here. And again, we don't know where this turning point is, and in advanced functions class, we never cared.